Yeah, thanks a lot, Mark. So I'll be talking about something slightly different. So I'll be talking about how ideas from integrated photonics can help rethink future acoustic wave devices and how this can influence future RF front ends. So most of this work has been funded by an EPSEC standard mode grant called Glimmer. So that's the work I'll be describing. Because of time limits, I'll mainly discuss the problem, our proposed solution, and what some of the hurdles that we plan to tackle are. But if you're interested in getting a bit more on the technical details of where we currently are on the experimental front, please don't hesitate to contact. So what's the main problem? So if you ask a bunch of device engineers what they think the key device contribution that has fueled the smartphone revolution is, you'll probably get a variety of different answers. But in my view, what enables modern smartphones is actually RF filters. And this is because compared to sort of older generation phones, what makes a smartphone smart is in some sense that in addition to being used as a cellular device, you're using it as your gateway to the internet, your GPS, even your credit card. And all of this is enabled just by having these multiple frequencies be able to carry out communication tasks in parallel. And if you look at a state-of-the-art cell phone, like an iPhone, it has on the order of somewhere between 40 to 50 RF filters. And as we move from 5G towards 6G, this number is only going to explode. And the other main challenge is that while the number of filters is increasing, at the same time, the amount of RF real estate that's devoted to filtering is actually roughly remaining constant. So you want more and more functionality from the same given area. So to look at this problem a bit more carefully, how do sort of modern smartphone filters, how is the filtering arranged in them? So usually you split the filtering into 3 or 4 frequency bands. So you have a low band, a mid band, and a high band. And for each of these bands, you sort of put together the filters, the amplifiers, and the switch network into these multi-chip modules. And the key thing to take from this plot is that as you go from 4G to 5G to sort of more advanced nodes, what you see is that not only the number of these multi-chip modules, but the complexity of these multi-chip modules starts to go through the roof. And this is illustrated in this plot from Carbo. And if you look at any state-of-the-art multi-chip module from the Qualcomm or Qualcomm, these are actually packaging marvels. And it's amazing what they're able to provide right now. On the other hand, there are limits to what you can do with this kind of discrete assembly of components. And this is a lesson that microelectronics has taught us for decades, that even though these things are complex, the complexity of what you can achieve is nothing compared to what state-of-the-art microprocessor can give you. And this is also a lesson that we have learned in silicon photonics, sort of my area, where again, once you're able to sort of put many of these things on the same die, the scale and complexity of things that you can achieve just goes through the roof. And we want to ask the same question. So why can't we do this for acoustics, or what best way to do this? So monolithic integration is not a new idea. People have been thinking about this for almost a decade. The standard solution has been to take the best electronics chip that is available and the best sort of standard FBAR filters and try to stack them together in some kind of sort of hybrid solution. The thing is, this works, and there are some commercial implementations of this, but the scale and complexity that you can achieve is actually quite limited. And this is true because aluminum nitride, while it's a CMOS compatible material, the two processes are sort of mutually incompatible, in the sense that electronics likes to be on sort of solid substrates just so that you can get the heat out. On the other hand, these FBAR filters require the substrate to be released so that you can get the acoustic quality factor. And so when you have to stack these two things together, in some sense, you're trying to put two sort of very different beasts, and then it's hard to process them inside the same sort of monolithic process. So, and that ends up limiting the sort of complexity of functions that you can achieve. So in this project, we want to ask, okay, what is it that you can do if you want to sort of truly achieve monolithic integration? That is, pack the filters and the electronics on the same die and sort of avoid all this substrate release issues. To see how that is possible, it's good to take a brief detour of what integrated photonics can teach us. And so the first thing is that if you look at a standard FBAR filter, this is one from Avago that I just picked at random, something interesting should sort of immediately become apparent. So these filters are roughly on the order of, so they work at around 3 gigahertz frequencies, which means that the acoustic wavelength inside this device is on the order of 1 micron. On the other hand, if you look at the size of this filter, this is like a millimeter on the side. And you can immediately ask the question, why is it that if your fundamental excitation is at 1 micron, why does the filter need to be 1,000 times larger? Or more precisely, why can't we build wavelength scale filters? And if you stare at this a bit longer, you can realize that the main reason is because you're using very weak confinement. And this is a lesson that all photonics engineers are aware of. So this is an optical fiber, and this is light being guided inside an optical fiber. And the key takeaway from this is that an optical fiber has very weak refractive index contrast between your core and the cladding. And so when you have weak index contrast systems, your mode sizes tend to be really large. So if you look at the x-axis, this is on the order of tens of microns. Now, if you take the same mode and you funnel it into a silicon photonics platform where the refractive index contrast, instead of being like 0.01 or 0.02, starts becoming 2 in this platform, you can see that the mode is now, the same energy is being carried in a much smaller form factor. So instead of being tens of microns on the side, you now have sort of sub-micron dimension waveguides. And this gives you a massive footprint advantage and enables monolithic integration. And the key message of our work is to sort of apply these same ideas to photonics. So basically, what we learn to do in integrated photonics, we want to do this for high frequency sound. And it turns out that gallium nitride is sort of an ideal platform for this, because gallium nitride is usually grown on either sapphire or silicon carbide. And in both of these cases, the speed of sound in gallium nitride is much slower than the speed of sound in silicon carbide in particular, which means that the acoustic wave and the acoustic energy is mostly confined inside the stop dimension, inside the stop waveguide. And now you basically have exactly the same scenario that you have with integrated photonics. You have a sort of wavelength scale structure. And the key question that we want to ask over the next 3 years is basically, how far can we push this analogy? And what is the scale and complexity of the circuits that you can build with sound? Things that we know how to do very well with light. Now, before going on to, I just want to spend one more slide talking about why this is an exciting time to work with gallium nitride and why some recent advances have enabled us to push this platform. The first is people have, not anything from the acoustics, but mostly from the RF and power electronics front. People have figured out how to grow thin films of gallium nitride, which is critical for us because we want to move to high frequencies, but grow them with very low defect densities. So when sound waves are guided, the main source of scattering and loss is the interface defect density. And now you can get substrates that have sort of very low defect density, or that is not the limiting factor anymore. The second thing is that if you want to do monolithic integration, you want to be able to put these things on the same die as the amplifiers. And it's very hard in a sort of academic environment to work on both the hemmed amplifiers and the filters at the same time. And so right now, you don't need to do that, because in principle, you can get GaN hemmed dies from a standard GaN foundry. And at Bristol, we post-process these dies to actually build the acoustic wave circuits. And finally, this is something that was originally a strong motivation for me, but I'm not an expert on this. But in sort of material systems replacements, you basically get sometimes a once in a lifetime opportunity where you can take a gallium arsenide power amplifier, but swap it for more than a like for like substitution. So you can replace a gas-based power amplifier with a GaN-based system solution. But there are some challenges here that I don't want to go into right now. But this is, if it works, it does promise a lot of great things. Now, at Bristol, all of this work was launched because of some initial experiments that we did when I first started here, which is that we were building these acoustic wave devices in gallium nitride, and we noticed that you can get really high acoustic quality factor in these substrates. So this is GaN on silicon carbide. And you can see that most of the acoustic energy is actually confined at the interface between the GaN and the substrate. And the very fact that you can achieve these very high quality factors means that the interface is good enough. And so once we saw these results, it became apparent that you can now push this technology towards three-dimensional confinement. Now, just to show, so as you might have guessed, I'm not an RF person. And so why is it that I got interested in this problem? This is not the main problem my research group focuses on. Our main effort in the group is to actually look at this problem of quantum transduction, where we want to take quantum states from, say, a superconducting qubit and translate them with high efficiency towards the optical domain. And effectively, the problem that we are solving on the RF front is just this exact problem in a different disguise. So to do quantum transduction efficiently, you basically need to be able to get RF signals from, in this case, a quantum source, say, a superconducting qubit. But ultimately, the interaction needs to be engineered in these small wavelength scale cavities. That's these photonic crystals that I've been looking at for ages. But you see that you end up with exactly the same problem. You have some RF signal source, and you want to be able to get this RF energy as efficiently as possible into some micron scale cavity. And you see that if you can solve this problem, you also solve the RF filtering problem. They're basically different disguises of the same problem. And so this brings me to Glimmer. This is the main project that I'm leading at Bristol. And so Glimmer basically has three key work packages that we are sort of focusing on. It's already time. Okay, yeah, just 2 more minutes. yeah, so the three main things that we want to do is that we want to sort of figure out what is the most efficient way in which you can put together these passive acoustic devices with sort of existing MTIs. My main interest is in actually pushing this photonic integrated circuits platform. So this photonics acoustic analogy and seeing where the limits are and where do things break. And finally, this is mostly driven by my interest in metrology. We want to invent new microscopes for visualizing sound propagation on a substrate. So the traditional Doppler vibrometers are not good enough for what we want to do. So we are inventing some new microscopes. And if you have any questions, I'm happy to answer that. And so the last thing I want to say is that, okay, what are the key hurdles, right? So, I mean, this all sounds very fantastic. So the main issue is that, yes, you can get this passive footprint advantage that comes for free in this process, but it's all for nothing if you can't get the performance inside the system. So there's no point getting 100x reduction in footprint if you can't get the same insertion loss that traditional RF filters have. And so loss is the main challenge that we are tackling, and we are tackling it on three main fronts. One is that we want to design better transducers that are both simultaneously impedance matched to 50 ohms, and you can sort of mode match to these wavelength scale devices. The mode matching itself is an issue by itself, and we are tackling that. And the final and sort of open-ended question here is that, is this way of building acoustic wave filters and resonators going to give you better performance than traditional FBARs? So just for the experts in the audience, most acoustic wave filters require you to confine sound using metals. And anytime you confine high frequency sound with metals, you get excess acoustic scattering loss. Whereas here you purely use whispering gallery modes, which confined by acoustic total internal reflection. So in principle, you should get higher Qs. This is true in optics. We want to answer the question whether this is true in acoustics as well. That's something we are working on. And so with that, I want to thank the team at Bristol. These are my co-Is for Glimmer. But most importantly, I want to thank the people who actually made this work possible. So with that, thank you, and I'm happy to answer any questions.
So thank you, Krishna. So if I can encourage the audience to pop some questions into the Q&A box, I could kick off. So in terms of the applications that you're thinking of, is it frequency band 1, which is sub 6 gigahertz, or are you thinking of frequency band 2, sort of the millimeter wave band?
Yeah, so right now, at least with the GaN, we can only, we are targeting the 3 to 6 gigahertz. That's primarily because gallium nitride's piezoelectric coefficient is not as good as lithium tantalate or lithium niobate. And there are other challenges with the sort of slow acoustic velocity that makes it difficult to go much beyond that. On the other hand, we do have some hybrid system platforms with diamond in place to just get the higher acoustic velocity to push this to beyond the 10 gigahertz range, but that's a bit more speculative right now.
So you mentioned a little bit about sound and vibration. So then it got me thinking, what's the mechanical and thermal stability of these devices if we're going to use them for filters in mobile phones? And I do drop mine occasionally.
Yes, so these are acoustic wave devices, but the acoustics is at very high frequency, so the net displacement of the surface is minimal, especially in a sort of solid platform. So that is not the issue. The other part is the more interesting one, which is what is the power handling capability and how much does the acoustic resonance shift. So that is something we are currently doing. So our current generation devices are not high enough quality factor that we can see these shifts yet. So we are able to put, like, I think at least a few milliwatts of acoustic energy through them without any issue. But once you start pushing the quality factor, or once you start bringing the loss down, then the sensitivity to sort of these parasitic heating effects start to become more critical.
Okay, but it's largely, well, it would really help on the receiver side if we improving receivers in mobile phones would make a hell of a difference to dynamic spectrum sharing and all these things. So
yeah.
Have you got any feel for what sort of insertion loss you're likely to achieve, or do you know what is your target for the insertion?
Yeah, so the target is to get to so for a standard filter is to get to sub 1 dB and at 3 gigahertz. So that's what we sort of so right now, just to give you some perspective, we are about we are at 20 dB inside.
Your receiver noise floor has gone through the roof.
Yeah, so but we are at 20 dB with a filter that is like a 1,000 times smaller. So there are some trade-offs that we want to explore. So this is the thing that I was saying. I mean, these are the very first devices, and one of the things that I at least found quite remarkable is the very fact that you are able to take sound, focus it into these very tiny waveguides and get it out, and you're also able to make them go around like long rings. And and be able. And so it's just this form factor advantage. And I don't know, as an open question, and this is hopefully useful to the audience, is that we want to ask the question if for example, it's very hard to imagine that you can build the same RF filters this way than you have traditionally, but you can build 10 times as many filters in the same footprint. So is there a new way to sort of rethink RF architectures in this way, where you don't have as many good filters, but you have many more sort of slightly less performing filters? But from a systems perspective, can you compensate in the same way? The same way that, for example, silicon gives you transistors for free, and you're able to compensate.
Yeah, we've been looking for disruptive technology in the way that RF transceivers are designed for years. As you know, I've been involved in signal cancellation or STAR. So yeah, fantastic stuff. Thanks for bringing that to us. And just for the benefit of those not so familiar with Bristol, Krishna runs an absolutely fantastic laboratory, and they've got the fabrication and the packaging to actually do this stuff in the city of Bristol. So do have a chat with him offline.